17 factorial, 18 factorial, 19 factorial, and 20 factorial. There we did it. I have accomplished my goal of calculating 64-bit factorial on this computer. This is it. As the title clip indicates, I have accomplished my goal of improving my PUTEY-1 Breadboard TTL CPU to be able to calculate a 64-bit factorial. As some of you know, well over a year ago, I discovered the Ben Eater SAP1 Breadboard TTL CPU series. I followed along and I built the SAP1 as Ben Eater described in his video series. But when it was done, I wanted to prove to myself that I had learned something. And to do that, I wanted to add capabilities to the Breadboard TTL CPU that I built. Now, I needed a guiding problem. That is, a problem that would focus my design choices and what I was trying to accomplish. And the guiding problem that I chose was to calculate a 64-bit factorial. And so I set out to improve my Breadboard TTL CPU to be able to calculate the 64-bit factorial. Now, there were many changes I had to make. I had to plot out all the various changes, from expanding the RAM and ROM to adding a stack pointer, even adding an LCD display that allowed me to display a 64-bit result. A 64-bit number could use up to 20 digits, and so I needed a display that could show up to 20 digits. The last change I need to make is to improve my Arithmetic Logic Unit. The original SAP1 uses Arithmetic Logic Unit based on the 74LS283, and while that is capable of doing many things, in order to efficiently calculate a 64-bit factorial, I needed to make some improvements. And so in this video, I go into the design choices and the hardware changes I had to make to my Arithmetic Logic Unit in order to update things so that I could calculate the 64-bit factorial. I cover mostly the hardware changes in this video. I don't go into the software that I had to write in order to calculate the actual factorial. I'll do that in a future video. But for now, I wanted to focus on the hardware, and there's plenty to cover there. So without any further ado, let's get into it. Let's go over why the original 74LS283 based ALU that the SAP1 has wasn't sufficient for my goals. The 74LS283 can only add two numbers. When combined with the 2's complement representation of a negative number, subtraction can be done too. The 74LS283 is only a 4-bit adder, but if you wire the carry out from one 74LS283 to the carry in of the second, you can do 8-bit addition and subtraction. To do 64-bit math in hardware, a total of 16 of these 74LS283s could be wired together. However, that gets expensive and would take up a lot of space on the Breadboard TTL CPU. But carrying the carry flag from lower byte additions to higher byte additions can be done in software. If the least significant bytes of a 64-bit or 8-byte value are added together first, then the carry out of that operation can be remembered and fed into the carry in of the next higher bytes addition. This can be repeated through all the bytes of the 64-bit value, from the least significant byte to the most significant byte. Now that we have a multi-byte addition and subtraction operation with two 74LS283s, the astute amongst you would say that I can do multiplication and division, because all multiplication is repeated addition, and division is repeated subtraction. And that's true. 64-bit multiplication and division subroutines can easily be built with 64-bit addition and subtraction subroutines. However, there's a major problem with this approach, and that problem can be illustrated with an example. Let's say we want to multiply 2 million by 4 million. The iterative addition algorithm will work, but it would take a very long time to complete because you literally have to do a few million addition operations. In computer science, we say that this algorithm is an order n algorithm, meaning that its complexity and effort needed to complete it grows linearly with the size of the value that you input to it. But fortunately, there is a faster multiplication algorithm that we can use. The faster multiplication and division algorithms are based on the fact that shifting a binary number left or right is the same as multiplying or dividing that number by 2. For example, take the number 5 in binary. If we shift it left once, which means effectively adding a 0 to the right side of the number, then the binary value becomes 10. Shifting it left one more, the 10 turns into 20. 2 left shifts is the same as multiplying by 2 twice, or put another way, multiplying by the second power of 2, which is 4. In this way, you can multiply any number by a power of 2 by shifting it left that power of 2 times. This raises the question of how do you multiply a number by a value that isn't a power of 2? Well, every number can be decomposed into a sum of powers of 2. And the easy way to do that is to just identify where that number has ones in its binary expression. That is, in fact, the very definition of a binary number. What powers of 2 are needed to be summed up to be equal the desired value. So the question then is, knowing this, what is the multiplication algorithm that can be derived? I'm going to show the algorithm here in Python due to Python's expressive clarity. The input to the multiplication algorithm are two numbers, a and b. Of these, you can pick either one that you're going to decompose into a sum of powers of 2. I'm going to go with b. An easy way to find the powers of 2 to compose b is to shift b right, and whenever the rightmost bit becomes a 1, that number of shifts to get to that state is a power of 2 that composes b. So here's a loop that does that. While b is greater than 0, that first line says we're going to be looping as long as b is greater than 0. The first thing we do is to check if the rightmost bit of b is equal to 1. If it is a power of 2. Then we shift b to the right one more time, and then we loop as needed. If at any point the right shift of b turns it into 0, we break out a loop and continue. Now, the multiplication algorithm is that for every power of 2 in b, shift a left that power of 2 number of times, and add the result to a running sum. After you found all the powers of 2 in b, that sum will be the multiplication results. Now, I don't have to separately shift a to the left n times for each found power of 2 in b. I can just shift a left in this loop here as we shift b to the right, and then only use a's shifted values when we are at one of b's powers of 2. That means the algorithm then becomes this. Here you see result is the running sum that we'll be adding the shifted a values into. We have the same basic loop that I just highlighted, but now when we find the rightmost bit of b is equal to 1, we add the current value of a into the results running sum. After that, in addition to shifting b to the right, we also shift a to the left. And when the loop breaks out, we return the result value, which is the multiplication result. And that's the algorithm. There's an important detail here that is not clearly showing in Python. The issue is because we are shifting a to the left, the resulting answer is going to need more bits to represent it than a needed. Or, more generally put, if a and b are both 8-bit numbers, the result could be up to a 16-bit number. This is because a could be shifted left up to 8 times because b itself has 8 bits. This means when you implement this algorithm in assembly, the result needs as many bits as the sum of bytes that compose both a and b. There's another detail I'm going to just mention here, but I'm not going to demonstrate. There's a way to rearrange this algorithm to transform it to only shifting right a value with twice the bits of the operands. It's doing the same thing as what I described above, but through the magic of rearranging the bits and bytes, you can have one shift operation rather than 2. This approach is actually what I implement in my code, and if you're interested, you can review the code more closely. I will also place a link to an informative blog post on this right shift only multiplication approach that I personally found pretty helpful when I was designing my code. Before we go any further, I'd like to point out that this algorithm is just the binary version of the very same long-form multiplication that you learned back in elementary school. The left shifting of the a value is equivalent to multiplying the top multiplicand by an intermediate digit and adding zeros to the right of the resulting partial product. And the adding of the a value into the running sum is the same as adding all those partial products to get the final multiplication results. So, if this algorithm feels familiar to you, that's the likely reason why. So we explored the multiplication algorithm in detail. A similar exploration can be done for division to find a similarly efficient division algorithm based on bit shifting. I won't go over that here, as I plan to go into details on that algorithm and how I coded both the multiplication and division algorithm in a future video. So now that we understand the bit shifting based multiplication and division algorithms, we can go over my specific design goals for my upgraded ALU. First, it should be just as capable as the current ALU that I use, which is based on Ben Eater's original SAP1 ALU. Simply put, this means being able to do addition and subtraction. Second, based on what I just described concerning multiplications, I would want the ALU to be able to do both left shift and right shifts of values. Furthermore, the carry flag needs to be supported to indicate when a bit is shifted off a value and used when chaining the shifts of multiple bytes together. So these two requirements should be obvious from what I discussed so far. Enabling bit shifting was the main motivator for this project, but there are some more improvements I would like to do while I'm improving the ALU. The third improvement would be to add the ability to do logical operations on bits. At a minimum, to be able to do a logical AND or an exclusive OR operation between two values. Fourth, I would like to be able to compare two values to determine which one is larger or if they're equal. Now, this could be done with a subtraction operation and then determining whether there was a borrow or not. The problem with that is that you need to place a value in an A register to do that. I would like to be able to compare any two values without needing to update the A register. The fifth goal is to be able to test the value of a specific bit for any given value. Like the previous requirement, I want to be able to do this without placing the value in the A register. This would be very useful when interacting with memory mapped devices, for example, when you want to check a particular bit in that device's status register. And finally, my sixth goal is to try to keep the chip count down. This may require me to use more advanced chips, but what I don't want to do is add a large number of breadboards just to accommodate a plethora of logic gate chips that are trying to implement some custom logic that the ALU needs. So now that we know what I want to design, let's go ahead and review what I did design. I ended up using KiCad's hierarchical schematic feature to keep this project organized. What you see here is the high-level design that shows the various main components of this advanced ALU. The 5 main components are seen here. First, we have the A register, which is also referred to as the accumulator. This component has two main responsibilities: hold the accumulated value for various ALU operations and perform the bit shifting operation. Next, we have the temp register, where adjunct values are placed for various operations. The third component is the core Arithmetic Logic Unit. This is where the operations for the addition, subtraction, and the various logic operations are performed. The fourth unit is the comparison unit. It implements both the magnitude comparison and the bit testing function. And finally, we have the flag register, which arbitrates and reports on the flagged outcomes of any ALU operation. With this project, I introduced two new flags, the overflow and the equals flag. These flags join the original 0 and carry flags to fill out the operation states that can be reported on. You may also notice this item up here labeled the ATF22V10C. Recall that one of my goals is to keep the chip count down. Given that this ALU is more complex, it is safe to assume that the logic needed to operate it is likewise more complex. I didn't want an explosion of logic gate chips, so I'm using something called a Programmable Logic Device to encapsulate all of that logic needed to control this ALU. I made a short video describing how these devices work, so I won't go into that here, but the short explanation is that you can think of these chips as an EEPROM for logic. So this ATF22V10C is responsible for taking a number of control lines from the CPU's control logic and converting them into a larger number of control lines that activate the various parts of the ALU components. Note that these input control lines are numbered S0 to S3. This is a set of multiplex control lines that together allow up to 15 different operations to be indicated. There are also a few other control lines coming in, like the A register in and the carry activate control lines. There's even an input from the carry flag coming out of the A register. All of these input control lines get translated into 10 output control lines that drive all aspects of the ALU components. And that logical relationship between these inputs and the outputs is programmed into this ATF22V10C. I will go over the details of that logic later in this video after I explain the individual components. Here's the schematic for register A. Central to this register's design is the 74LS194 shift register. This chip allows you to load a value, write that value out, and shift that value either left or right. It is a 4-bit register, so 2 are needed in order to make the A register 8-bit. The operation that the register does is controlled by 2 control lines, A_S0 and A_S1. When only A_S0 is high, a left shift is done. And when only A_S1 is high, a right shift is done. And when both A_S0 and A_S1 are high, then the value on the data bus is loaded into the register. These control lines are driven by the Programmable Logic Device I discussed in the ALU overview. This logic here controls the reporting of A register's carry flag. A carry flag is only reported if a shift operation is requested, and depending on which direction the shift is, the leftmost or the rightmost bit in the A register is reported as that carry flag. The temp register is a fairly straightforward register. Two 74LS173s, which are 4-bit registers, are used to hold and report the value in this temp register. This register is similar in design to the registers that you would find in the Ben Eater SAP1. The ALU is deceptively simple. It is centered around two 74LS382 4-bit Arithmetic Logic Unit and function generator chips. These take input values from both the A register and the temp register. The result of the operation is reported to the data bus through this bus transceiver. These 74LS382 chips can do addition, subtraction, logical AND, OR, and exclusive OR. The exact operation to be conducted is controlled by these ALU S0 through ALU S2 control lines. These control lines are also driven by the programmable logic device I discussed in the ALU overview. The 74LS382 generates both the overflow and carry status flags. More details about the 74LS382 can be found in the short video that I did on the chip. There's one more chip here, the 74LS682 magnitude comparator. These chips take two 8-bit value and reports if they are equal and if not, which one is larger. I use this chip to generate the 0 flag by comparing the output of the 74LS382s to 0, which is generated by simply grounding all of the pins for one of the inputs to the 74LS682. Then the equality output of the 74LS682 is used to drive the ALU 0 flag. The comparison unit has a lot going on. It can do 3 types of comparisons. It can compare the data bus value to 0, compare the data bus value to the value in the temp register, and determine whether a specific bit on the data bus is 0. To do the 2 data bus comparisons, I use the 74LS682 again here. One side of the comparator is connected to the data bus through this bus transceiver. If you look closely, you can see that this bus transceiver is always on. I'm only using it to isolate the comparison unit from the data bus. The other side of the 74LS682 is connected to the temp register output, but that output is moderated by another 74LS245 transceiver that is controlled by the CMPS control line. When the CMPS control line is selected, the transceiver pushes the temp register value through to the comparator. When the CMPS control line is not selected, the output of the transceiver goes to high impedance, and so these pull-down resistors set the comparator input to 0. In this way, the comparator can compare the data bus value to either the temp register value or 0. This logic here reports the comparison equality to either the 0 flag or the equals flag, depending on which comparison operation is being done. The 74LS151 here is an 8-to-1 multiplexer and is used to do the bit testing function. The data input to the multiplexer comes from the data bus, and the bit selection is set by the 3 lowest bits in the temp register. The multiplexer can then report the selected status. Note that I am using the inverted status. In this way, it is reporting whether the bit is 0 or not. The reason I did it this way is I didn't want to create yet another type of flag for the bit testing operation. I'm reusing the 0 flag and is semantically the same as the 0 flag. So when this bit is tested, the code would branch based on the 0 flag. Here is the flags register schematic. One of the first things to notice is that it also uses an ATF22V10C Programable Logic Device. This programmable logic device is used to arbitrate all the various flag lines and propagate the correct one based on the operation being conducted. For example, note that there are 3 different 0 flags. One from the ALU module, one from the value comparison unit, and one for the bit testing. The ATF22V10C uses the flag control lines to determine which one of these 0 flags should be used to set the system's 0 flag in the 74LS173 register. The flag control lines are actually set by the other ATF22V10C being used to decode the system control lines into specific operations. So for example, if the system control lines indicate that the addition operation is being done, the main ATF22V10C will activate the ALUF control line, which then tells this flag register's ATF22V10C to only pass through the ALU0 flag to the 74LS173 register. Before we move on, there's one more detail to look at. This 74LS245 bus transceiver here is used to allow the flag register value to be written to the data bus. The reason I did that is to allow for the saving of the flag state for later testing if needed. I don't quite have a use case for this yet, but I figured while I was updating the flag register, this would be a good time to do that. I did consider being able to write to the flag register from the data bus. However, I wanted to minimize my chip count, and that would have required more chips than I was willing to add. So, let's look at how I designed the logic for the programmable logic device that arbitrates the inputs to the flag registers. Here is the PLD code for the flag registers ATF22V10C. The logic for this chip is relatively simple. There are 5 outputs. 4 of those outputs are the 4 flag inputs to the flag register, and the 5th output is the enable signal to the 74LS173 used by the register. For each of the flag outputs, the logic is saying only use the flag inputs from the source that is currently active. This is done by ANDing a flag input with the flag activation line coming in from the main ALU control ATF22V10C. Note that in this code syntax, the asterisk means and the addition operation means or. So for example, the carry flag output line is only active if the A register carry flag is active and the A register flag activation line is active, or if the ALU carry flag is active and the ALU flag activation line is active. Then finally, the register enable line is configured to go low when any of the flag activation lines are active. The / in front of the register enable line symbol means to take the inverse of the value. So when used in this manner, it means to set the line low when the equation is true. Otherwise, the line should be high. Since the 74LS173 register enable line is active low, this is how we want the line to behave. Similarly, here is the configuration for the main ATF22V10C used to control the overall ALU. As you can see, there's a lot more happening in this ATF22V10C. The main inputs are the S0 through the S3 control lines that come from the system control logic. Those control lines, in combination with a few other inputs, are used to determine what ALU-specific control lines need to be activated to affect the desired operation. I'm not going to go over every detail in this configuration. I will say there are 3 main parts: logic that pertains to the A register, the ALU and function generator, and the comparison unit. This file is in this project's GitHub repository if you wish to inspect it more closely. The link is down in the description. I made a few more changes to my PUTEY-1 design with this project. The first is I updated the system control logic to use the 2 new flags being reported. Now, the control logic uses 0, carry, equals, and overflow flags to control which instructions is being selected in the microcode. I had to make a corresponding change to my microcode generation script, which was to simply enable these flags in the instruction microcode definitions. The second change is to the increment registers I and J. As you might recall, I made these registers a few videos back, early in my journey of designing the PUTEY-1. These are additional general purpose registers that have the added ability to increment or decrement the value they contain. The core chip used for these registers is the 74LS169 up-down counter chip. Watch my original video on these registers for details on how to use the chip. So what changed with these registers is that originally I added some logic to do the 0 and carry detection for the increment and decrement operations that these registers can do. In this version, I took that logic away. The motivating reason for this is that I now have the comparison unit back in the new ALU that can compare the value on the data bus to 0. So I can now do the 0 flag check on the increment and decrement operations by writing the I or J register's value to the data bus and executing a comparison to 0. This is done in the microcode for the register's increment and decrement instructions, so from an assembly code perspective, there is no difference. I did make the design choice not to try to replicate the carry flag detection that was originally made for these increment registers. The reason for that is that carry detection was complicated since there was no native support for that in the up-down counter chips, and simply put, I never used it in my code. 0 detection was much more useful for these increment registers. One thing I will add here is that the HL register, which is the PUTEY-1's 16-bit increment register that can write to the address bus, now has 0 flag detection for its increment and decrement operations. This uses the new comparison unit too, and is also done in the microcode for the HL register's increment and decrement instructions. There are a few more changes made to the PUTEY-1 in this project, such as updating the step counter and improving the memory map controller. I go over those changes in detail in my GitHub repository. The link will be down in the description. Here's my PUTEY-1 Breadboard TTL CPU updated with the advanced ALU I just described. The layout is roughly the same, but I'll go over the changes. Here is the A register. This is where the bit shifting occurs. This is the new logic unit, the one that has the 74LS382s that does the addition, subtraction, the OR, ANDs, and exclusive OR operations. This is the temp register. This is the new comparison unit right here between these chips. And finally, the I and J register down here. You can see the wiring where the temp register is feeding down into the comparison unit as I described in the schematics. So that's everything I wanted to cover in this video. In the next video, I'll go into the details of the software I wrote to take advantage of the PUTEY-1's upgraded ALU. I will go over the details of both the multiplication and division algorithms and how they get coded into the PUTEY-1. But before I end this video, I wanted to show that it works. I set out to implement a 64-bit factorial algorithm, and I've done that. I've burned the code into this ROM right here, and we'll just have to watch it run. So let me go turn this on. There you go. It's calculating factorial. Now it's going rather fast because I did update the clock speed on this to about 480 kilohertz. Getting close to the maximum 64-bit value. 17 factorial, 18 factorial, 19 factorial, and 20 factorial. There we did it. I have accomplished my goal of calculating 64-bit factorial on this computer. While we're looking at my TTL CPU run, let's zoom in on the memory map controller status LEDs to see something interesting going on. The LEDs in the middle are the memory map control line status indicators. As you can see, there are two of these LEDs that are periodically blinking. The LED on the left is the memory map 2 control line, which I'm using to drive the LCD display. The LED on the right is the memory map 15 control line, which is the 1K memory map I/O block I defined in my prior project that implemented the memory map controller. I haven't found a use for this block yet, so it is unused. This immediately raises the question, why is this LED glowing? At first, I thought something was wrong, but when I hooked it up to an oscilloscope, I immediately realized what was going on. To understand, let's look at the memory map controller schematic. As you can see from the memory map controller schematic, the memory map 15 control line is enabled when both the memory map enable control line and the address line A10 are high. Now, take a look at this oscilloscope reading of the clock line and the memory map 15 control line. You see that the memory map 15 control line spikes for a very brief period right when the clock goes low. So what happens when the clock goes low? That's when the CPU updates its control line configuration for the current instruction and step counter value. Looking at the schematic, note that when an address line change occurs, that change has to go through 3 layers of logic gates before the memory map enable signal is updated. However, the memory map 15 control signal has only 1 layer of gates if you ignore what is behind the memory map enable line. So what is happening here is that when the CPU transitions from a step that has the memory map enable control line high, like when we are writing to the LCD display, to a step that doesn't have the memory map enable control line enabled, but does have the address line A10 active, then there is a short period of time when both the memory map enable control line and address line A10 are high, thus causing this AND gate to go high and in turn causing the memory map 15 control line to activate. This high level lasts only as long as it takes for the memory map enable control line to turn off. Measuring that time with an oscilloscope reveals that it only takes about 50 nanoseconds for the memory map enable control line to turn off once the address lines have been changed. This is in line with what you'd expect based on the datasheets of these logic gates. It turns out that this LED flash was occurring at all clock speeds. However, at slower clock speeds, the aggregate time that the LED is on across any given period of time, such as a second, is insufficient for your eyes to detect the light. However, now that I'm running the PUTEY-1 at 480 kilohertz, the memory map 15 control line LED is on for a sufficient amount of time for the human eye to be able to see it. Anyway, I thought this was an interesting detail and wanted to share. While there is certainly an aesthetic issue with seeing the memory map 15 control line glow despite it not being used, it is not interfering with the desired operations of this CPU at the clock speeds that I intend to operate it, so I'll leave it be for now. So that's it for today. If you enjoyed this video, please give it a like. If you want to see more videos like this, please subscribe to my channel. Hopefully I can get the next video out much more quickly. But until then, goodbye for now.